Page 7 of our Chapter 6 review. So 25, real quick, anytime they want to change the angles, the figures will no longer be similar. So B, C, and D are all out. So the two things that must remain true is that the corresponding sides have to have the same ratio, and the corresponding angles must be congruent. So B, C, and D all suggest the corresponding angles can change, so they're all false. The ratio was in fact 4:1. Okay, 20 over 5, if you factor out a 5, is 4:1. Which polygons are always similar? Equilateral triangles have to be. Trapezoids, they don't have to have the same angles. Okay, you can have trapezoids without the same angles. Rectangles, even though they'll have all angles 90 degrees, you could have corresponding sides that are not proportional. So equilateral triangles, they all have 60 degrees. They all have the same side lengths. All right. So which pair of triangles must be similar? I can find right triangles that have different angle measures. Same with obtuse. Yeah, same with scalene. The only thing I can't do is I can't have isosceles triangles with different base angles if their vertex angles are congruent, because triangles have to add to 180. So as soon as the vertex angles are the same, the base angles are forced to being the same. So it'll be A. Okay. So there's a couple ways to complete 29. I would probably graph it, but I'm going to just explain it first. A way to do this is to move from the center to the pre-image and figure out what that movement is. So to go from 4,4 to 2,3, I would have to go left 2, down 1. Okay. Now the scale factor is 3, so I should triple that. Okay. So if I want to go from the center of the image, it would be left 6, down 3. Now I'll do the algebra on that. Left 6 is like subtracting 6 from x. So that's going to take us to -2. Down 3 takes 3 away from y. So it's going to be -2, 1. Okay. I'm just going to show it over here on the graph as well. Okay. What you can see is the slope is down 1, left 2. Or you could call it right, up 1, right 2. So what I'm going to do is I'm going to repeat that 2 more times. So down 1, left 2 once. Okay, down 1, left 2 a second time, and down 1, left 2 a third time lands A prime at -2, 1. Okay, so now we get into our dilate lines. What we have to know for these last couple is slope is always preserved under dilations. So if we dilate a line, you're going to get a parallel line or the same line because slope's preserved. Slope, same slope means parallel. So now, since the center is at the origin, I knew that this line did not hit the origin. So because it's the origin, I could recalculate the y-intercept using a scale factor of 4/3. So I'm just going to end up doing that. First, I got the slope of the original line is actually +2. Okay, because you have to get it in y = mx + b format. So I'm going to multiply the current y-intercept. The current y-intercept is 6. So I'm going to say 6 times 4/3 is 8. So then my new equation is same slope, so y = 2x, 2 in front of x, and then plus the new y-intercept, which is 8. Okay, 31's kind of a trick in a way. If you start out by trying to graph it, you're going to find that the center is on the line. The moment you find out that the center is on the line, you don't have to do anything further. You just state, okay, so it's the same line. Now, the individual points definitely move, but they create the same line. So we could just right then know it. I did it algebraically instead of graphing. When you plug in the coordinates to the equation, if both sides work out, then it's on, that point's on the line. So 6 is equal to 6, which tells us 210, the center of dilation is on the line. The moment you figure that out, you know the equation of the image because it's the same exact line. All right, that's it for chapter 6 review.